Okay, this right here is the data from the Tektronix TDS3054C. This machine will do 10,000 samples across the screen on each channel, so that's 30,000 samples. Channel 1 yellow is the timer shunt, showing what the timer is drawing. The blue is the power shunt, showing what the load is drawing, and this is the battery voltage. These numbers are just ballpark indicators. It's showing that the load right here at 1.8 waveform, so it's chopped off, is negative 30, and then 462 millivolts RMS at 1.5 megahertz, and the timer shunt is showing a negative 3.82 volts. So together that appears to be, based on these ballpark numbers, that the battery is receiving a net gain while the circuit is running at no cost. And so if that's what the numbers mean or not, I'm not really sure, but this is what we're going to do with the data. So this right here, we have 10,000 samples of channel 1, 2, and 3. 1 is yellow timer battery shunt, channel 2 is load shunt, and 3 is battery voltage. So what I'm going to do is I'm going to just put a couple rows in here, or columns, and in this one I'm going to do the 555 wattage draw. In this column is load watts, and we'll put those down at the bottom of the screen. Okay, so for right here, what I'm going to do is, first of all, I have to delete some samples here, because this, all I want is from one point of the waveform starting to where it ends. Now you can see that it actually settles below 0. Okay, it's not settling from 0 up, it's starting from a negative and going positive. But what I'm going to do, just for simplicity, is I'm going to start this sample at where it starts going positive on the upswing for this on pulse. And where I'm going to end it is the same place, on where the next waveform begins, where it goes and hits positive and goes up. So on this side, I'm robbing myself of this amount that's negative, but I'm making up for it by getting it back by leaving this in on this side. And it's just you see from 0 to a positive, so it's absolute, no guesswork. And so what I'm going to do is channel 2 here, this is the load, and you can see that it's negative right here, and then it switches on, and then it starts going positive. And it starts going positive right here, which means the first 96, and I'm just going to make a note of that, 96 samples will have to come out. At the very end, this is 10,000 samples across the screen. This is at the 600 mark, or 6 out of 10 mark, which means that the this full complete waveform ends at 6,000 samples. So what I'm going to do is come down to 6,000 samples, right around 6,000 samples. Okay, and it's negative, and what I want to see is where it starts going positive. So it starts going negative, 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 and then it starts going positive. That corresponds to where this spike is heading up right here. And so what I'm going to do is I'm going to grab that positive and take it all the way to 10,000 samples. And I'm going to delete that because that's not part of the waveform. That starts the next waveform. Then I'm going to go back to the beginning, and at waveform number, or at sample number 96, that and below is negative, but the positive on the upswing starts here at 97. So I'm going to delete those 96 waveforms. Okay, and what that left me is exactly from the upswing of the first one to the upswing right here, or actually below where the next one starts positive. So I got it at the exact two same reference points, so I have exactly mathematically one complete waveform right here. So what I'm going to do in column C to calculate the wattage for the timer is that these voltages are across the 0.25 ohm shunt for the timer battery draw, showing what the timer is running on. Okay, and so what I'm going to do in this column is find out the timer wattage requirement. And so I'm going to put it in a sum here, and that cell, actually B2 is the cell with the voltage for that particular time frame, for that particular voltage on the battery for the timer shunt, showing what its draw is. So B2 divided by 0.25 ohms on that resistor, and I'm going to multiply it by F2, which is the battery voltage, and I got that many watts. And what I'm going to do is I'm going to grab it and I'm going to drag it down through all almost 6,000 samples. Okay, I passed it up. Okay, right there. So this column C is all the wattages for each 5,000, almost 6,000 samples with a corresponding battery voltage at each of those times. And so what I'm going to do there is take the sum and I'm going to divide it by 5,880, not 5,881, because I left the first row, which indicates the names of the columns. So anyway, the sum of all those wattages divided by 5880 equals negative 0.06578 watts. So it costs nothing to run. Okay, now we're going into the load watts, and same formula except for the column in E. So we're going to go E2, which is the voltage across the load shunt, divided by 1 ohm, because it's a 1 ohm shunt resistor, for ease of the math, and then multiply by F2, which is the battery voltage for that particular time. And then I'm going to take that, I'm going to drag it down through all 57 or whatever 100 samples. Pass that by a long shot. Okay, right here. Alright, almost got it. Okay, right there. Okay, then I'm going to get the sum of that, and I'm going to divide that by 5880 samples. And we have a negative 0.0682 watts that the load is running on. And so this, I'll just make a little space here to make it easier to see. This is the 555 watts. This is the load watts, and then total watts that this whole circuit is running on. If I add what it takes to run the timer, and if I add what it takes to run the load, that's the total that the battery has to supply to the circuit, and that sum is a negative 0.13406 watts. This is showing that these waveforms are negative in nature, negative dominant, and there's more going on below the line than above on the wattage. Real negative power. This is negative energy, possibly. And so what I'm observing on the circuit is that the load is actually running at a negative 0.8 Celsius below ambient, 0.8 below ambient. The shunt, the 1 ohm shunt, is running at the same point. It's 0.8 Celsius below ambient. Ambient's 25 Celsius. The resistor between the battery and the timer positive that I'm using to adjust how much power I'm letting to the timer, that is running at 28 Celsius. I'm sorry, it's at 8 degrees above ambient, which is 32 degrees, 33 degrees. 8 above ambient. The 555 chip itself is running at 5 above ambient, so 30 degrees Celsius. The MOSFET is running at 1 above, so the MOSFET is 1 above ambient. The 555 chip is 5 above ambient. The resistor that I'm varying the power to the 555 timer from the battery on the positive rail is 8 above ambient. The load and the load shunt is running at a 0.8 Celsius below ambient. So anyway, this is the calculations based on what the Tektronix TDS 3054C was able to sample, and this is showing that there's a net loss of minus 0.13406 watts, which means conceptually the battery should be gaining energy while there's cooling on the load and the load shunt, but there's warming on the timer part of the circuit. RMS at 1.5 megahertz, and the timer shunt is showing a negative 3.82 volts. So together that appears to be, based on these ballpark numbers, that the battery is receiving a net gain while the circuit is running at no cost. And so if that's what the numbers mean or not, I'm not really sure, but this is what we're going to do with the data. So this right here, we have 10,000 samples of channel 1, 2, and 3. 1 is yellow timer battery shunt, channel 2 is load shunt, and 3 is battery. Okay, this right here is the data from the Tektronix TDS3054C. This machine will do 10,000 samples across the screen on each channel, so that's 30,000 samples. Channel 1 yellow is the timer shunt, showing what the timer is drawing. The blue is the power shunt, showing what the load is drawing, and this is the battery voltage. These numbers are just ballpark indicators. It's showing that the load right here at 1.8 waveform, so it's chopped off, is negative 30, and then 462 millivolts